Good day. In today's discussion, we'll be exploring the concept of heat transfer. But before diving into that, let's first define what is heat. Heat is a form of energy that flows from an object with a higher temperature to one with a lower temperature until both objects reach thermal equilibrium. Imagine placing a pot of water on a stove. The stove generates heat, which warms the pot, and eventually the water begins to boil. This entire process is known as heat transfer. There are three modes of heat transfer: conduction, convection, and radiation. Conduction is the process by which heat is transferred through a material without the movement of the material itself. It happens when molecules in a hotter area of the substance collide with molecules in a cooler area, transferring energy between them. For example, when one end of a metal spoon is placed in a hot cup of coffee, the heat travels from the hot end of the spoon to the cooler end through conduction. After a while, the entire spoon becomes warm. The equation for conduction is Fourier's law, where quality of heat is equal to negative thermal conductivity multiplied by open parenthesis change in temperature over change in thickness of the material. Let's try solving this problem using Fourier's law. A metal rod with a thermal conductivity K is equal to 200 watts per meter degrees Celsius is 1.5 meters long and has a cross-sectional area of 0.01 meters square. One end of the rod is kept at temperature of 100 degrees Celsius while the other end is at 30 degrees Celsius. Calculate the rate of heat transfer through the rod. We are given the following values. Thermal conductivity is equal to 200 watts per meter degree Celsius. Length is equal to 1.5 meter. Cross-sectional area is equal to 0.01 meters square. Temperature difference is equal to T1 minus T2. So 100 degrees Celsius minus 30 degrees Celsius is equal to 70 degrees Celsius. So this will be the value that we will be using for temperature difference. Since the heat flows from the hot end to the cool end, the negative sign can be omitted. Now let's substitute the known values into the equation, wherein Q is equal to 200 multiplied by 0.01 multiplied by open parenthesis 70 over 1.5 close parenthesis. This gives us 93.33 watts. So the rate of heat transfer through the rod is 93.33 watts. Conduction is the principle behind insulation. Materials like foam are used to reduce heat flow from the outside of the house to the inside during summer. So, why are materials like metals a good conductors, while wood and rubber are good insulators? I'll leave you with this question. Now let's move on to convection. Convection is the transfer of heat through a fluid, a liquid or a gas, by the movement of the fluid itself. When a fluid is heated, it becomes less dense and rises, while cooler, denser fluid sinks, creating a circulation pattern that transfers heat. For example, when you heat a pot of water on a stove, the water at the bottom warms up, it becomes less dense and rises, while the cooler water at the top sinks. This continuous circulation of water helps eventually distribute the heat throughout the pot, causing the entire water to eventually reach a boiling point. The equation for convection is Newton's law of cooling, where Q is equal to heat transfer coefficient multiplied by the surface area for heat exchange, open parenthesis, surface temperature minus ambient temperature, closed parenthesis. Let's try solving a problem using Newton's law of cooling. A flat metal plate is exposed to the air at temperature of 25 degrees Celsius. The surface temperature of the plate is 75 degrees Celsius. The heat transfer coefficient for the air is 50 watts per meter square degrees Celsius, and the area of the plate is 2 meters square. Calculate the rate of heat loss from the plate to the surrounding air. Our given values: surface temperature of the plate is equal to 75 degrees Celsius. Ambient temperature is equal to 25 degrees Celsius. Heat transfer coefficient is equal to 50 watts per meter square degrees Celsius. And the area of the plate is 2 meters square. Now let's substitute the given values into the formula, wherein Q is equal to 50 multiplied by 2 multiplied by open parenthesis 75 minus 25 close parenthesis, which gives us 5,000 watts. So the rate of heat loss from the plate of the surrounding air is 5,000 watts. So, why does a hot air balloon rise? That is for you to find out. Now let's move on to radiation. Radiation is the transfer of heat through electromagnetic waves, like infrared radiation. Unlike conduction and convection, radiation doesn't require a medium, so it can occur in a vacuum of space. For example, the heat you feel from the sun is radiation. Another example: the heat from a campfire travels to you through infrared radiation, allowing you to feel warmth even if you're not touching the fire directly. The equation for radiation is the Stefan-Boltzmann law, where Q is equal to sigma, the Stefan-Boltzmann constant, multiplied by surface area through which heat transfer occurs, multiplied by epsilon, the emissivity of the surface, open parenthesis temperature of the surface area to the fourth power, minus the ambient temperature to the fourth power, close parenthesis. The value of sigma is equal to 5.67 times 10 to the power of negative 8 watts per meter square Kelvin to the fourth power. Emissivity is a measure of how efficiently a surface emits radiation compared to an ideal black body. It ranges from 0, which is no emission, to 1, a perfect emitter. For real objects, emissivity is often less than 1. According to Stefan-Boltzmann law, the rate of radiation increases rapidly with temperature. Specifically, the radiated power is proportional to the fourth power of the object's absolute temperature. Now let's try solving a problem using Stefan-Boltzmann law. A metal plate with an emissivity of zero point 0.8 is at a temperature of 600 Kelvin. The plate is exposed to an ambient temperature of 300 Kelvin. The plate's surface area is 2 meters square. Calculate the net radiative heat transfer from the plate. The given values are surface temperature 600 Kelvin, ambient temperature 300 Kelvin, emissivity 0 0.8, surface area 2 meters square, and our Stefan Boltzmann constant, which is 5.67 times 10 to the power of negative 8 watts per meter square Kelvin to the fourth power. Now let's substitute these given values. Q is equal to 5.67 times 10 to the power of negative 8 multiplied by 2 multiplied by 0 0.8 multiplied, open parenthesis, 600 to the fourth power minus 300 to the fourth power, close parenthesis. Let's first calculate the temperature. 600 to the power of 4 minus 300 to the power of 4 is equal to 1.215 times 10 to the power of 11. Now let's calculate the net radiative heat transfer. Q is equal to 5.67 times 10 to the power of negative 8 multiplied by 2 multiplied by 0 0.8 multiplied by 1.215 times 10 to the power of 11 is equal to which gives us 11,022 watts. So the net radiative heat transfer from the metal plate is approximately 11,022 watts. The Stefan Boltzmann law is essential for calculating radiative heat transfer, particularly when dealing with high temperature objects or situations where radiation is the dominant mode of heat transfer, such as in space. It shows the strong dependence of radiative heat transfer on the fourth power of the temperature difference, highlighting how significant temperature changes can greatly affect the rate of heat transfer. Why does a black shirt feel warmer in the sun than a white one? It's because black absorbs more sunlight and converts it into heat. The black color absorbs all wavelengths of light, while a white shirt reflects most of the sunlight. As a result, the black shirt accumulates more energy and heats up faster, while the white shirt reflects energy and stays cooler. To end our discussion on radiation, I'll leave you with this question. How does the Earth's atmosphere trap heat through radiation? Why is it important to understand heat transfer? Understanding heat transfer is important because it allows us to use and design more efficient systems, save energy, and maintain comfort in various environments. In engineering, it's necessary for designing like buildings, machines, and electronics that need to control temperature. In daily life, it helps with activities like cooking, heating, cooling, and insulation. It is also essential for addressing environmental challenges such as reducing energy waste and minimizing the effects of climate change. That ends our discussion for heat transfer. Thank you for listening. I am Anna Jane Gio, your MAST student.